we'll mention it again for record here. We're going to first finish off the last few slides in the lecture. The slides after we talked about cellular automata. And we're going to talk about the subject of the lab today, which is modeling diffusion using capability suitability modeling, turning capability suitability modeling into diffusion modeling. So marrying those two concepts. Basically what we're modeling here is we're still modeling how capable or suitable a particular phenomenon is, but what we're doing is changing it to, does it exist, to how fast will it grow under certain conditions. So there's an element that can be used to model the growth, the actual growth, as a function of time. Okay. So capability suitability modeling asks the question, what will be the spatial extent of some phenomenon? Where are all the locations it could occur? Okay. Temporal modeling, when we bring that into the equation, we're asking the question, we're answering the question, when will the phenomenon reach a certain spatial extent? All right, so we still have some similar important elements. Notice that the second bullet I have listed here is factors. Factors are something that we talked about when we did capability suitability modeling. But in addition to that, we have to specify what we call an origin. Where is this particular phenomenon set to diffuse from? Where is it going to be the starting point? Okay, and that can be any sort of a map data that we want it to be. It's typically a raster data set, and that's particularly for this class, where the values are either yes or no. It exists or it doesn't exist. It exists at this point. Okay, the origin will become useful in the feedback. Okay, similar to what I tried to get started last week or last time we met on Tuesday, but we're gonna get that to work this time in the lab. All right, the factors. Now, factors will contribute to or tell us about how suitable a particular landscape is for diffusion. And what we mean by that is that the factors have to be expressed in terms of growth rate. Okay, so there has to be an equation that represents how. So the end result is that it equals growth in some units. Okay? Growth meaning millimeters per month or yards per day. So it's a linear unit divided by a time unit. That's what has to happen. So precipitation causes so much growth. We'll show a formula here in a second. Maybe that'll make a little bit more sense. Also, we can add in barriers to diffusion. Barriers to diffusion can be permeable or impermeable. In other words, they can slow the growth rate down a lot so that they're effectively a barrier, or we can make a barrier. We can have a barrier layer that represents areas where this particular phenomenon cannot diffuse. There's no chance of it diffusing. And another important element is if any of your factors have a temporal nature to them, like for example, what we're going to do in the lab today, we're going to model the growth of a plant diffusing over space, and that plant actually won't grow in certain weather conditions. Okay, the temperature gets too low. We can't use annual precipitation to model the growth of that, because at some point it would be able to grow, and some points it will be dormant. It won't be able to grow. So your your data also has to have a temporal nature to it. You can't have a single input unless that input never changes over time. So if you can assume that that particular input layer is constant, then you don't really need it, a temporal set of data. But if that thing like temperature is changing at every time step, you need what those values would be at every time step. Okay. So how do we actually implement what I'm talking about? Well, in this case, this type of diffusion modeling really builds on two different concepts. Okay. The first we've already discussed, capability suitability modeling. The second is cost distance modeling. Remember what we did in cost distance modeling? We created a surface where the surface represented the time that it took to get back to the source based on based on cost, a cost layer. So that was the output to that data set. Well, in diffusion modeling, using capability suitability modeling, the goal is to create a surface. We're going to call it a rate surface, and it gets created in the same manner as the factor surface, except for now, it's the time that it takes to get to a certain place. The time that it takes to get from the source to a certain location away from the source. So if you look at the slide here, I almost went over and pointed to it, but if you look at the slide here, here are the basic steps here. So we can take a rate of movement. So let's say we've got 100 meters per day in a forest. So this might be the diffusion rate of just somebody walking. Okay, 100 meters per day in the forest. They could go 200 meters per day on bare land, and they could not move on a lake. Okay, that's a very simple rule. So they can go twice as far on bare land as they can through a forest. And we're gonna model the diffusion as they go out away from a source. Okay. So these are the steps that you could do to take that. So you reclass the movement rate. The movement rate would be the cost. The 100, 100, 200, 200. Okay, that would be the distance that they could travel through the cell. Okay. Now, how does that differ from cost? Okay. It's almost inversely proportional, right? A 100 is lower cost than 200, but we're not talking about cost. We're talking about movement rate, growth rate. Growth rate or movement rate, those terms are interchangeable here. Okay. So if we say a 200 movement rate and a 100 movement rate, 200 is twice as fast. But if that's a cost rate, and we're going to use cost distance modeling for this approach, those numbers won't work. And so to turn a movement rate, which is in distance units per time, in other words, here it's meters per day, we want to turn that into something that's more like a cost. So we can divide 1 by the movement rate. So instead it'll be 1 day per meter. It'll be days per meter instead of meters per day, because we're flipping it by saying 1 over. Okay. So now we've got time per unit distance here. Okay. So we take our rate surface. Sometimes people ask in this course, and it's a good question, how do we make a rate surface? That's a good question. Lots of times as a GIS expert, I work with scientists in different fields. And so a scientist from a different field might have studied this particular plant and knows its growth rate. Or they look at historical maps, or you could look at historical maps of the same plant diffusing in another area and try to come up with a rate. Okay. Right. So we come up with a movement rate, take 1 over that movement rate, and then if you input this layer, this time rate layer, into the cost function, what you'll get is the cumulative travel time. Okay. So every cell will represent the amount of time it takes to get from the source to that cell. So here we've got 0 starting at the source, and as you go out, it takes 40, whatever the time units are in. Okay. Days, months, years, whatever they are, you've got that value. So this is 40 days to get from here to there if these are in days. If they're in minutes, then it's 40 minutes, and so on. You control the time step. That's actually one of the kind of hang-ups. Because you control the time step, there's some requirements. I'll go back to that other slide in a second, but the third bullet here, remember the time step must be small enough that the phenomenon can move at least 1 cell during the time step. Otherwise, you won't be able to model it. Okay, if it's not moving 1 time step, it'll never change. All right. So there's now we have to deal with spatial resolution and temporal resolution. Okay. This is the generalized. This is the generalized approach to what we're talking about. This is how to actually implement it in a raster GIS system. Okay. So we have our origin. Our origin says where this particular phenomenon is starting from. Okay, where is it starting from in the world? It's a raster data set. And then we have our factors that influence diffusion. Maybe precipitation here is listed. Maybe temperature. Those are the 2 ones we're going to use for our purposes today. But it could be population. It could be land cover. There could be lots of different factors influencing diffusion, and some of them may or may not change at every time step. Okay. If we're modeling land cover, land cover does change, but at a much different scale than precipitation and temperature change. They change on yearly cycles. Okay, so our factors that influence diffusion. Some mathematical formula needs to be established that turns our factors that influence diffusion into an actual movement rate. Okay, so that's some sort of formula. In our lab, that's going to be a given. Okay, we're going to give you a formula for taking the factors that influence diffusion and turning them into a movement rate. Okay. Then every cell will have a value that represents the movement rate in that cell. How fast the stuff in the origin will diffuse through that cell. Okay. The next thing is that that movement rate is just turned into distance per unit time. Well, that's the movement rate. It's turned into time per unit distance. So this is where the formula is that takes the factors, turns them in to distance per unit time. Then we divide that we divide into 1. So 1 over that to give us the time per unit distance. Okay. Then we run the cost distance function using the source using the origin as the source. And what we'll end up with is the time to reach each cell in this period. In other words, every cell will have the time that it would take this particular phenomenon to diffuse through that cell for that time period. Okay. And what you'll notice is that there'll be some cells, lots of cells, that couldn't be reached in that time period. So let's say it's a 30-day time period. There'll be lots of cells that have values of 50 and 60 and 70. What does that mean? Well, that means that for this particular time period, the phenomena is not going to reach that particular location. It's not going to happen. And so we reclassify this so that we say, okay, all the areas that were under the time period, less than or equal to the amount of time, those are the new origin. That's where the phenomenon got to. That's where it reached after this point. Okay, and so then we take that and that becomes the feedback, the new origin. That becomes the feedback loop into the new origin, and then this process just continues and continues each and every time. Okay, it loops around. So the new origin loops around here. If the factors need to change, they change here, and they feed in. Okay. I just wrote it out over here. It's not much different. All right. So, like I said, you need to be able to, your phenomenon needs to be able to grow. So you need to establish a cell size that's small enough or a time step that's small enough that your phenomenon actually makes it out of the original cell. And by the way, the cell size and the time step will influence your results. And so whatever formula you come up with in the first one has to be has to match your chosen time step and cell size. All right, so that's what we're going to do today in the lab. So I just kind of went over it. Probably make a little bit more sense when we actually implement it here. Okay, so what I want you to do is open up ArcMap, and if you go to the course website, this is where I explain again what I was talking about here. If you go to the course website, labs, and you download temporal modeling, I couldn't get the data in there. It wouldn't let me put the data in there for some reason. So we've got just the text of the lab, and we've got a toolbox that I've written. I made a toolbox for you to use. Okay. And we'll go over that toolbox here in a second. To get the data for the lab, go to the U drive on the computers that you're at, the U drive. Does everybody know what the U drive is? If you don't, it's not a problem. It's a brand new thing that we just started earlier this semester. Okay. Everybody knows what the U drive is? I don't have the U drive on this computer, so I can't show you. But if you go to the U drive, inside the U drive, there's a folder called SA. Should probably make it something better than SA, but it stands for spatial analysis. Okay, go into that folder, then go inside the SA folder and copy week 8. Copy the week 8 folder out of that folder. Make sure you make a copy. Don't use that that folder directly, because you're going to mess up everybody else if you use that data as your working data. So make a copy of that. This has become a really popular number to call recently. Okay, so make a copy of that and save it onto your computer. I think I did that. Nope. Let me get my local copy. So I've got my local copy, labs, lab 8. I'm going to copy that and put it on, I'm just going to put it right in the root. It's probably not the best idea, but okay, so it's already there. Yep, okay, lab 8. C lab 8 is where I've got it. All right, so if you open up lab 8 and look at it, you'll see what we're going to do. All right. So you're going to copy the entire folder in your working directory. We've already done that. It's kind of funny that I put that in there because you can't actually do that until you can't actually see it until you do that. All right. So if you look in that folder, we've just copied a bunch of files. There are actually 25 grids. there are 12 temperature grids and 12 precipitation grids, and then there's a single, I guess it's not really a grid. There's a shapefile actually, or a feature class in there. So you've got those values. The units for the temperature grid are in Celsius times 10. So in other words, a value of 30, which is a really pretty warm day, would be 300 in this thing. So the way you can read it is, if it said 300, it would be 30.0 degrees. If it said 301, it would be 30.1 degrees. Okay. The other set of grids are average precipitation for each month, and the units are in millimeters times 100. I guess that would be meters, right? Millimeters times 100. The last grid is a source representing, oh, no, sorry, millimeters times 100. That would be like super millimeters. Or I'm going backwards, sorry. The last grid is a source representing the introduction of a hypothetical noxious weed. Oh yeah, so there are 25 grids and there's a feature class as well. Okay, so there's 26 data sets in there. All right, your job is to execute the temporal model steps. I'm sorry. That will show the diffusion of the weed based on the following criteria. So this is the criteria. This is basically the formula that we need to use every time through the loop that will be used to create our movement rate or our growth rate. Okay. The weed's not going to spread into areas that have a temperature less than 21 degrees. It's approximately 7 degrees Fahrenheit. Other than this, this constraint, weed is not affected by temperature. Okay? So it won't go into areas that are less than 21 degrees. But other than that, that doesn't affect the growth rate. Maybe it's not realistic. It's a simplification for our purposes. There should be a comma there. Other than this constraint, maybe I should say the weed so that it doesn't sound like I'm talking about marijuana, right? All right. The weed is, all right. I didn't mean for it to sound like that. The weed is very influenced by the amount of precipitation that it receives. It diffuses at a rate that has been determined to be 1 meter, I should say 1 meter per day, for every 10 millimeters of precipitation. Okay, and the weed's going to be introduced in June. So those are going to be our constraints. All right. So if you read the rest of this, it's just saying, I've already created kind of a recipe that we're going to go over, and you're going to implement the recipe. Okay. Not that you couldn't create a toolbox like this, but I have something for us to start with this time. So if you go to C, Lab 8, or wherever it is on your disk, and what I'm doing is adding a toolbox. Sorry, I should have shown that slower. I right-clicked on toolbox and said add toolbox. So you'll get to where you have this toolbox there. Did I go too fast for everybody, or have you been able to open up the Temporal Modeling Lab toolbox there? All right. So if you go to edit this, you probably really don't need to edit it too much, but if you go to edit it, that's just the format I had it laid out in. I hesitate to hit this because sometimes it doesn't look like I want it to look. I guess that's not horrible. So let's look at what it's doing. All right. So I know we've done this in the past, but I've set up these as parameters so that when the user clicks on the tool, they'll be able to specify the precipitation and the temperature, okay? And so the first thing, let's look at temperature first, because temperature, remember we said that the only thing that temperature did was say that it could not grow in areas where the temperature was greater than 21. In our case, we have to write 2100 because it's it's been multiplied by 100 in the initial data set. So this just says the temperature value is going to be greater than 21. And so what are we going to get in the output values? We're going to get a bunch of values here. I didn't specify a false raster. And so we're going to get a bunch of values of 1 and a bunch of no data values is what we're going to get. Okay? Because I specified that here. So 1 is the true value. In other words, if this conditional statement evaluates to be true, it'll get a value of 1. If it's evaluated to be false, it'll get a no data value because I didn't put anything here. Okay? So we'll get 1s and no datas. It's kind of just like a mask, because if we multiply anything by no data, we'd get no data. And you'll see what we'll do eventually. We turn that 1 into a float so that it's 1.0, and then we multiply it by what's coming down this pipe. And what's 1 times anything? Right. And the reason why I made it a float is because this number is not always going to be a nice round integer. And the way ArcGIS treats it is if you multiply 1, an integer, by 7.5, it turns it into either 7 or 8. I forgot which one, but it rounds it off for you. So I didn't want that to happen. So 1.0 times 7.5 is 7.5. So that's why I turned it into a float there. Okay. So that's this line. And then we all know, or we've said before in this class, that no data times anything else is no data. And so the output of this data set is a bunch of 1s and no datas. And it's no data where that particular phenomenon cannot diffuse. Okay? It can't diffuse at that point. So it makes sense to multiply those areas by no data and say there's not going to be any growth in those areas. Okay? So that's what happened. That's what this line is all about. Very simple line. Really, we're just trying to find out, was it above or below that threshold? This line here, see this line here? We have to put this other formula in, which if we look at that, that formula here is 1 meter per day for every 10 milliliters of precipitation. So we look at this divide sign, and we get precipitation divided by, and here's the constant value 10. Okay, and that works out because of the extra zeros on one end. Okay. So that's that number, and we get an output that will basically be the this is just 1s turning into a float. Yeah, so this is just a bunch of 1s. Okay, this creates a raster full of 1s. Okay, that's all this does. So I give it a value of 1. I turn that into a float grid. I float the whole thing, and there's my output. And so I'm taking my movement rate, which is right here, and I'm saying 1, which is coming in from here, 1 divided by that output from this set. All right, and so then I take the output of that and I multiply it by this other data set, so that basically I just get no datas where it can't grow. I get no datas where it can grow. I mean, I get the same value where it can grow, and I get no datas where it can't grow. All right, and so then the next thing to do after that multiplication problem, I have my final growth rate. I then use the cost distance function. I don't need the backlink, so I just get the output distance here. And the final thing is that because I expressed my growth rate in how far it could get in a day, and my time step is months, I have to do this conditional statement at the end that says, okay, if it took less than a month, and I used 31 as the day, really, so what I'm saying is, if it took 30 or less days to get there, I'm going to call that a month. Now, if I was really precise, I guess I could modify this parameter every time through the loop, this 31. So you have I could make it 32 on the months that had 31 days, and I could make it 29 on the days that had 28. But for our purposes, we're just going to leave it at 30. Well, 31, which means that it'll be 30 days or less. Because the average amount of days in a month is pretty close to 30. Okay. All right. So that's that model. So let's run it. So close it. You don't have to save it if you don't want to. I mean, it'd probably be best not to save it in case if you went in there and you actually accidentally typed a button or something, it would fail if you do save it. So let's go ahead and we don't really have to add any data yet, but let's before we run the model, let's look at some of the data. So I said that it would begin in June or July. June, so that's 6. So let's load up temperature 6 and the source. I'm going to hit the control key. Temperature 6. Not having a. There we go. Source and then precip 6. So we're going to add those 3 data sets in. Okay, so this is climate data, and notice that unlike the interpolation lab, I did put this in a real projection. This is even more important today because we're actually modeling growth in a linear unit. And so modeling growth as degrees would not make much sense. So I put this in a conic projection. It's a good nationwide projection. Obviously, there's still some distortion, but it's much better than having the having this in a projection that was not appropriate for the source or for the modeling effort. All right, I'm going to put source up on top. Move it up there. All right, and my source is, I'm going to turn the symbology to red so you can see where it is. Still won't be able to see where it is till we zoom in, but yeah, you might be able to see that if you had really good eyes. Make sure you eat your carrots there. Okay, so there it is, right kind of close to Cape Fear. If you didn't see where I zoomed in, there's the dot. That's the source. That's the originating location of this particular weed. And we can see the temperature grid. If we turn that off, we can see the precipitation grid. And each time through, these values change. If you want to load all of the climate data in, you can. You can see that it changes every month. All right. So let's do one cycle. So if you double click on this growth cycle script, you'll see that you can specify which input grids you want to put in there. So you could specify your temperature grid, your precipitation grid, or the precipitation grid from the data, and then you could specify your source grid. Now, one thing that you need to do, let's just save this in the same folder we've been working on, Lab 8. I'm actually going to make a new file database and call this outputs for organization purposes. Save it in there. I'm going to call this out_6. All right, just because it's the output from June. Okay, one thing you need to do, it won't work unless you do this, is if you go under the environments, you need to change the processing extent and the cell size in order to be the full extent of the data. Otherwise, every time you do it, it'll only do the extent of the minimum extent of the grids, of all of the grids together, which so the growth will never leave a certain place, and it may even give you an error. But this is a vital step. So go under processing extent and change this to be any of the grids, because they're all the same. They're all the same extent, but any of these grids. So I'm going to choose temperature 6. I'm going to change my snap raster to temperature 6 as well. I'm going to change my raster analysis cell size to temperature 6. And don't change mask. Okay, mask will cause it to basically mask out anywhere that's not a true value. So don't change that. Only change cell size, snap raster. Snap raster is not vital. If you didn't change that, it's not a problem. But what that does is it makes it so that the cells actually have the exact same centers. It snaps the raster to the existing raster. Theoretically, if you take the cell size and the processing extent and you set both of those, it should create a raster in the exact same spot. So that's why snap raster probably isn't important, but I'm still setting it anyway. Okay, so I've set all those things. If you don't, it'll fail. It probably will fail, and it definitely won't work. Okay, so I'm going to say okay, and let this run through. And when it finishes, you'll see, so it's doing all the steps inside the model. So we hit cancel. Oh, sorry, not cancel. We hit OK when it finishes. Don't hit cancel. All right, it finished right there. It created that output 6. I'm going to hit close. And if I zoom in, you can see, put this up at the top. You can see that it grew into that area. Those are the areas that grew, and it grew a little bit further this way. We can measure that. Okay, that distance is a lot of meters. Just remember it's 37862, and this direction is 37074. So it didn't grow quite as far in that direction. And remember that precipitation is the main factor there. It's hard to tell, but evidently there must be slightly more precipitation growing this way. Now we're gonna see as we continue, there's not as much precipitation up here, and that's going to affect the growth rate. There's more precipitation down here. So as we continue to do this, we'll see the growth change. In fact, let's do that again. So how will we model this the second time through? Well, we'll open up growth cycle. Now you can either load it into the view, or you can just pick it off of disk. Let's go 7 for the temperature and 7 for the temperature, or precipitation. Sorry, I chose the wrong one. Precipitation, 7. And then for the source, what are we going to change? Yeah, the output from the last model becomes a source for the next one. And that's the way it's going to continue to go. Okay. So notice in this particular modeling technique that our inputs change each time through. That didn't really happen with the cellular automata. And then our source changes each time through. That did happen. We did do that in the cellular automata approach. Okay. And then now we're going to specify our output as out 7. This will be the output at the end of July. Okay. We hit save, and again, we have to make sure that the processing extent has to change. You can still choose temperature 6. It doesn't matter because they all have the same extent. So temperature 6, cell size is under raster analysis. Change this to temperature 6, hit OK, hit OK again. It's going to run through. Okay. Oh, why did I do that? Okay, I'm going to hit OK again. I hit cancel. I was just impatient. It does take a few seconds to run. And then it has that. All right. Now it's completed. Okay, so now look where it's gone. It still looks fairly uniform. Okay, there's not a whole lot of change. It is slightly longer in this direction. Okay, so let's continue on. So we've got we're now going to choose temperature 8. I'm just going to copy. I guess that takes almost as long. So, but you could do this. Precip 8. The source is now going to be the output from 7. And the result is going to be output 8. Right? Okay, 8, 8, 7, 8. Good. I've got to change the environments again. I've got a way I'll show you that you don't have to do that. Hold on a second. We'll do that the next time. So if we hit temperature 7, temperature, it doesn't really matter. Temperature 6, as long as it's one of the grids that you've already run. Raster analysis, cell size, temperature 6. Okay. So then I hit OK, run it again, and I'll get precipitation 8. I mean, output 8. Okay, once this finishes, I'll show you what I mean here. Okay, I'll hit close. There's 8. Now we're starting to get a little dent right here, okay, because there's less precipitation going on. Well, we're not looking at the 8th month, but there must be less precipitation right here than in this direction. You get a little bulge here and a little dent in our perfect square. I mean, our perfect sphere or circle. Okay, if you go to geoprocessing and results, if you click on a previously run tool, the environment variables stay. So you don't have to change them. So see what I did? I just clicked on this previously run one. And the nice thing here is all I need to do now is up these numbers manually. 9, 9, 8, 9, and then I'm set. See, I don't have to change the environments because they're already been set. So I say OK, it runs through, and it will create the output for the 9th month, which is September. Don't hit cancel. All right, close. I'm going to zoom out just a bit. Okay, it still looks fairly uniform, but again, we've got this dent here, and eventually, what we're going to see. So let's run it a few more times so we get into winter. So I'm just gonna do this. You don't have to. You should be able to Follow this along pretty well. I'm not going to make as many comments here. So this will be the end of October. So the end of November. I'll take this through January because I want to show. I want to kind of show something that will be necessary to understand for the next part. All right. $12. 12, 12, oops, 11. All right, now in January, what's going to be different? Because we're going to cycle through the years. So what's going to happen differently? Well, how do we say January? That's just one. So now we're going back into January. But our outputs, we're going to keep going because we're just enumerating the number of months since we started. Well, in this case, 6 since we started. So if we go back to 1, eventually we're going to get back to 6, and that's going to be a problem. Okay, so our outputs are going to keep going up in a normal numbered sequence, is what I'm trying to say. We probably should have started our outputs at 1, so that would always be like months since starting. Okay. All right. So now at the end of this, it'll be January, and we'll look at the results. So we've got our data, and it's kind of upside down. Let's flip it back so that we can see what's been going on. Okay, see that? So that's what's been going on, and you can see that for the most part, it's growing like a ring. We don't have very many things influencing our data, but you can definitely see that, first of all, it's starting to grow slower. See, through the last part of the months, and in fact, it stopped growing altogether. Actually, in year 10, it stopped growing altogether. See that? I mean, in month 10. So month 10 is not any different than month 11, 12, or 13. Okay. Why did that occur? Well, maybe let's look at temperature 10. So now temperature 10 here. Okay, it's not quite cold enough to stop it from growing, but the precipitation must be low enough that it doesn't grow a full month. I mean, it doesn't grow a full cell in a month. So it's stopping it completely. Okay. All right, so the growth slowed down over time, and you can see in some areas it grew less. Like there was something blocking it here, slightly less precipitation. Okay. See, they're not perfectly concentric rings, is what I'm trying to point out. Okay, so what does the lab say? Well, we're going to, what you want to do is follow that recipe through 12 times, ending in May. Okay. Right. We really only need to save the new source each time, which is what we've been doing. One thing to do, let's think about what if we wanted to express this growth in a single data set. We could do that. I didn't mention this in the lab, but what happens if I take each of these data sets and add them together? I'm not going to save this anywhere special because it's just going to be what I show for a second. Never mind, that didn't work. Okay, why didn't that work? Well, because there's a bunch of no data values. The only place that I get data is where they all overlap. I could fix that. If I did a is null statement and turned all the no data values into zeros, I could add them all together and I'd have a single data set where 1 meant that it had only been in that area for a month, 2 meant that it had been in that area for 3 months, 3 meant that it'd be in that area for 4 months, and so on. So it would show that. Okay. But I didn't put that in the lab. That would be something that you could do. I wanted to point that out. Okay, so we got some questions. So what's the extent after 1 year of growth? Express that answer in grid cells. How would we find that? That's a pretty straightforward question. But how do we know how many? So this is after, this one right here is after how many months? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So we're almost done. How do we know how many grid cells are in that affected area? How can we find that out? What's that? The table? Yeah, exactly. Any table that is of any grid that's an integer grid will have a table associated with it. And we could simply look up and go to the, the table. I double clicked. You do right click on it and you do say open attribute table. Okay. So we have a value of 1 and we have a bunch of values of no data, but here's the count. So how can we convert that into area? If we did want to convert it into area, the total area that had been affected by our noxious weed, there's the grid cell count. How would we turn it into area?
You can multiply the area of the single cell.
Exactly. Multiply the area of the single cell by that value, and you get the total area. Okay. All right. Okay, operationally, how can we modify our model if it were found that this weed would completely die out and not be capable of spreading if the average temperature reached 15 degrees? In other words, it wouldn't just go dormant, it would die. How could we change our model so that it would model that effect? So let's look back here. Here's our growth cycle. We edit this guy. Okay. We want to say it's going to completely die out if the temperature is less than 15. So we need something. How would we? What kind of tool would we use to find out if the temperature was less than 15? How do we do that? Yeah, we could use a conditional statement. We could put a conditional statement in that said, if the temperature is less than 15, assign a 1. Do the same kind of thing. And then assign a no data if the value is not less than 1. that's not what I meant to do. I mean, sorry, if it is less than 15, assign a value of no data. Okay, so we have our ones and our no datas. Where would we put it here? Where would we multiply it in to our model? Would we multiply it into our model the same place we put this other constraint? Or would we put it somewhere else? Think about what the question states. I mean, what the thing states. It says it's going to completely die out in areas where the temperature is less than 15. Completely die out. That's the key here. What happens when our new source goes into the next model? We assume that it's the new extent of the weed. So, oops. So if the weed died out, we might want to put that towards that side. I'll let you all dwell on that for a little while, but it's not a factor that's affecting the growth. It's a factor that's actually affecting the next input, right? So that's the key to answering that question. Okay. If you put it in here somewhere, where would you put it? But do you have any ideas, you can come talk to me. All right. And we input in a model builder approach, which was probably better than pressing all the buttons manually. What advantage would there be to automate the entire process? In other words, wouldn't it be nice if you could just press a button, or put a few inputs in and then have it run the entire process? Yeah. Okay. So that's what part 2 of the lab is all about. Okay, we're gonna attempt to do what didn't quite work. Didn't quite work Monday. I think I have a better handle on it. I mean, not Monday, Tuesday. We're going to put a for loop. We're going to create a new tool and put a for loop in it. One of the nice things about Model Builder is once you build a tool, you can actually put your tool inside of another tool. Okay, so that's what we're going to do. It's, rather than putting the for loop in this model, probably what we should have done on Tuesday anyway, is you build the model that you want, then you take that model and you put it inside of another tool where you have the for loop. Okay? So model inside of a model. I'll show you what I mean right here. Don't pay attention to this for a second. We'll get to that. All right. So I'm going to close. Oops. Close down that. I'm actually going to remove all of the output layers that we created. Source isn't even really important. Okay, so here is our temporal modeling lab. What I want you to do is create a new model, and we're going to call this model, well, something else. That doesn't matter what we call it right now. Let's just leave it like it is. All right. Now here we are going to pull the growth cycle tool onto this model. In other words, this growth cycle is what we're going to run. We're going to run that, and inside this box is still the entire growth cycle model. So you can put a model within a model. Okay. And then I'm going to right click here and say make variable from parameter temperature. Okay, so I've got my little temperature box. And I could specify a value here. Okay. But we're not going to do that right off. Okay. But this is how I could actually run. If I wanted to just run this model inside of a model, I could do that, but that would be silly because then we could just run the original model. But that's why I created those things as model parameters. The temperature, the things that I made temperatures were, parameters were temperature, precipitation, and source. Those are going to be the inputs. All right, so let's do the for loop that we started on Monday and Tuesday and it didn't quite work. So what I'm going to do here is I'm going to insert model only iterators, a for loop. Okay. And for right now, I'm just going to start at 6 and go to, I'm only going to go 3 months. I'm going to go 6 to 9. And it's going to increase by 1 every time through. Okay. So from 6 to 9. Eventually, we're going to make this model run a bunch of times. Okay. Let's see if I put it exactly in there. Yeah, it still just says to go for a year, but we could go even more. Okay, 6 to 9 by ones. Say okay. All right. Now we do have to do that. We do have to do that calculate value tool. We still need that from earlier. So if I go to that was actually under here. Model tools only, calculate value. Our calculate value tool will calculate a new value for us based on this value. This value here will change each time. It'll be 6 the first time, then it'll be 7, then it'll be 8. I'm not sure if it'll actually go to 9 or not. Probably will. I don't. We'll test it. Okay. All right. So let's say that the calculate value tool is going to take this value as an input. Now, when we try to connect it, okay, and we say expression, that will work. Let's see what it says. The expression value type variant. We want it to be that value each time through the loop, though. And what this is going to do is just pass the value through. We actually want to change it into a full path. And the other thing that I forgot to do in class last time is that we actually need to change this to the data type that we want it to be. In this case, we want it to be a raster data set for input to the next time through the model. Because we want it to be the input here. We want to be able to connect this up. Okay. So our data set, our expression is going to be a little bit different. What we want to do is copy the path to our data. Okay. So that is, whoops. Let's open up, can I get to our catalog? No. I'm going to open up our catalog so that, I can copy the path exactly. Just because I'm a bad speller. Lab 8, climate data, Control C. So that's the path, and then we're gonna type the this path is a Python expression, okay? And we do have a course where we talk about Python more, but in order to get this to work, you have to type R, and then a quote, and then the path, you're going to type in TMP underscore quote plus, and then here is where you're going to type in percent value percent. What it's going to turn into, what it's going to evaluate to is this text plus the value in here, which is going to be each time through the loop is going to be 6, 7, 8, 9. Okay, R quote the path to the data quote, then a plus sign, then percent value percent. And the percent value percent is the name of this variable. The other thing I messed up was naming it n. Just leave it value or call it something else, but don't call it n, because that'll mess you up. And make sure this says raster data set. At this point, you can hit OK. Yeah, you just R, then the quote, then the string, then another quote, plus percent value percent. Okay. Then we're going to connect these two and say that it's a precondition. What happens there is value has to have a value before calculate value will run. Another thing that I'm going to do is rename this TMP for temperature. That's not necessary, but I can rename it. Now, what I'm going to do here, I'm going to go ahead and delete growth cycle for a second, save my model, and run it. Okay. Sorry, I forgot this part. STR percent value percent. Because it's a Python expression. And in Python, the way you convert an integer, which the value is an integer, to a string is to use this syntax. STR percent, STR parenthesis percent value percent. Okay. So now hit OK. And then try to run it. And it should run. So the value, the first time through, see how this is going to be C equals lab 8, climate data, GDB, temp 6. That's good. I'm going to say model run entire model, because that worked better. Okay. So now it says temp 9, temp 8. See where it says here, temp 8. So it's creating it each time through. Temp 7, temp 6. So it's created that output. Now that's just the temperature output. So we have to do this for the precipitation as well. So let's say insert and say model only tools, calculate values. And we're going to do almost the same thing. So I'm just going to copy the code. I'm going to copy it from the first one. Say copy. Say OK or cancel. And then we go in here and paste it. Except for this time, we'll change temp to precip. And we'll take this variant type and change it to raster data set. Okay? So it should look like that. Almost exactly the same, but you say precip instead of temperature. All right. Okay, then you say OK. And again, you'll have to, well, you don't have to, but I would, rename this precip. And then you will have to right-click and say, or sorry, you have to connect value to calculate and set it as a precondition. So now you've got your temperature and your precipitation data sets being created each time through the loop. I'm going to go ahead and save it now. All right. And I'll say model, run entire model, and I should see that it's creating both precip 9, temp 9, precip 8, temp 8. It's doing that. Temperature 7, precip 7. Great. All right. Yeah, you got a question?
Yeah, can you open up that calculate value one more time?
They look almost the same, so I'll just open up the one here. Wish I could make that bigger for you. R. Okay, I'll tell you what the just so that you're not in the dark here. Slash in Python is actually what they call the escape character, meaning that the slashes all get removed, and like for example, /n means new line, and /quote means I want to use this quote inside of a quote. And so if you use the R before, what you're doing is saying ignore all the slashes. Just the slashes are real slashes. I want them. And so that's why you have that R there. Okay. So that's the mystery behind why the R is there. Otherwise, if you left that R in there, Python would remove all the slashes unless like /L or /C means something. /T I do believe means something. I think it's tab. So it would put a tab there. It would insert a tab there instead of a slash. So that would be bad, because then it would say there's nothing called climate data tab temp. All right. So that's what that's for. We've got all that. We can say okay here, and we're all set to go. Now, let's pull our growth cycle back on here. Okay. And what we're going to do is connect temperature down to the growth cycle and say that's the temperature. And we're going to connect precipitation down to the growth cycle and say that's precipitation. So now if I double click on the growth cycle, those are filled in automatically. If I were to drop down, I can do the same thing. I don't know if we've talked about this before, but the little recycle sign with the blue means that we're using something from this model. The little yellow square on its side means that we're using a data layer that's loaded into ArcMap. We definitely do not want to do that in this case. Use the temp with the recycle sign. All right. So that's the growth cycle. Now the output of our growth cycle is going to be our source, but first we also need to specify our source. Okay. And so what you'll do here is go in here and say create variable. We're going to create a variable. We're going to call it, we're going to make sure that it's a raster data set like the others. So it's right there. We're going to take this data set and we're going to rename it source. Okay. And then we're going to choose the source data set. We're just going to choose it. Make sure you go find it on disk, not through ArcMap. Okay, so it should be blue after you do that. And you should be able to connect it into the growth cycle and say that this is the source. All right. Okay. The next thing that we're going to do here is we're going to change the output to okay. Another thing that's difficult for ArcGIS to do is to have a source also be the input for the next loop through. Okay. So in other words, if I went like this, and connected this into here, it's going to say, it's going to use that as the feedback for the next loop. And when I tried this last night, it didn't work. I had to make a copy of it before I did that. But let's look here real quick. What I'm going to do is change this so that it outputs into the output folder. Here's out 10. I'm going to change it so that instead of out, I'm just going to call it output, so I don't delete those previous outputs. And then I'm going to try to say percent n percent. So it's going to be the nth time through the model. All right. Like I said, last time this didn't work. I had to create a copy of it first. But I'm going to try it because I was using an older version of the software. I'm going to say model, save, and then I'm going to close it. Right now, I don't have any parameters set. So when I close this model and then I go to run it from here, it's not going to let me change anything. It's not going to let me change the time I start, the time I end. But I'm going to choose my environments and make sure I set those right. I need the processing extent to be temperature 6. The snap raster, again, to be temperature 6. It just needs to be a raster that's the full extent of what you want it to run. The cell size, temperature 6, and don't set the mask. Okay, I'm going to try to run this. See if I get the same problem. And if I do, then I'll quickly fix what I did. Let's see what it's doing here. So I'm on 7, output 1. Okay, it's made it past where it failed. So I think this is working. We'll have to look at the outputs to make sure. It's basically gonna take. Remember how long it took to run one cycle before? It took about 10-15 seconds. Well, we've run it 5 times, or sorry, 3 times now. And so it'll take about the same time to actually run as it would to run the model 3 times. So I did 6 to 9. So it's at least 3, maybe 4, depending on whether it goes through a few times or not. So this might be the last time through, depending on whether it does 9. Yeah, so it is doing, looks like it is doing 9. Cost distance is the one that's taking a little while. See that, how long that takes? Okay, so it completed. So I hit OK, close, and I'm going to see what my outputs look like. If I go into Lab 8 outputs, that's where I put them. I'm going to load up 0, 1, 2, and 3. So it did run for 4 months. And change each of these. Wow, they got such descriptive lilac. Okay. All right, so yes, it worked. It did the exact same thing, and it did work today. I thought it should work. So let's go back and edit it. So that what I did when I connected this through, it knew that this was executing after this one, and so it knew that that had to be a feedback. But if there was different choices, it would have said, "Do you want that to be a feedback?" If I click on this, or right click on it and display the properties, it tells me that it's a feedback. Okay, it's a feedback. And so it's going back into the loop as the source. Okay. Now, it should become a little more clear now that I could put that constraint of if the temperature is less than 15 degrees, I could put that right there, okay, before the feedback occurred. See what I'm saying? Like, if I said everything where it's 15 degrees or colder, it's going to die out. It's like I have to remove those areas from the source. See what I'm saying? So that would be where I'd put it. Now, I told you to tell me where you'd put it in the other model, in the growth cycle model. But you can see that it has to be on one of the ends. All right. So this now works, and it should work for you. If it doesn't, are you using? Did it work for you guys? Did it work for you, Hilton? Okay. Did it work down on the coast?
No.
You got some errors. Everybody got some errors. Now down on the coast, you're using the same version of software I'm using, so it's not software based. So we'll have to find out what's going on the coast. Up here, it might be software based because you guys are using 10.1, which is what I was using last night. Okay.
I got it working.
You did get it working. Okay. So, of course, I know I moved one of those. Do you know if you're using 10.1? Okay. I know the computer next to you is using 10.3 because I upgraded one of the computers. But anyway, yeah, we'll get everybody's working. I'll come around. All I did to fix it. Maybe there was something else wrong with my model last night, but I copied that data set out, so I had an additional copy here before it went on to fix it. So that's one thing to try, but we'll look at yours in a second. Okay, so let's look at the final assignment here. Oh, before we get there, you do or you should realize that there's a problem. And the problem is that this will only work as long as the months keep incrementing. So 1, 2, 3, 4, 5. When we get to 12, the value is going to change. We want the value to go, we want the month input to go from 12 back to 1. Okay, see what I'm saying? 12 back to 1. And I couldn't think of a way to solve this problem other than to use a little snippet of Python code. Okay. So I'll show you what you have to do with this Python code and in your model to get it to work. So and then we'll go around and get everybody's working. Okay, so if you take your calculate values, this is going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, up to, so to do a full year, it would just be impossible. You'd have to do it in like 2 steps and start up again. So what we have to do is to copy this text right here, this code block text, hit Control-C, and copy that into here, Control-V, okay? And this return, blah, 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 that can be copied from this. That's the path. So you get it's going to return that, and then we're going to take this line of code and put it up here. So what this does is it says, okay, this is going to be a function. It's Python. It's a function that I made up. I called it makePath. I called my function makePath, and this is the Python code that it gets executed for makePath to happen. Okay, the input is going to be the value. Okay, 1, 2, 3, 4, and all this function does is it takes the value and it gives me the remainder after dividing the number by 12. That's what this is called this percent sign is called the mod operator in Python. So it gives me the value after taking the remainder. So if the value is, if 13, what's 13 divided by 12? Just, you don't have to give me the integer of 13 divided by 12. How many times does 12 go into 13? It's not a hard question. One time, exactly. But what's the remainder? Okay, well, we haven't probably used remainders for a long time, but what is the remainder? 1, exactly. So if 13 is the value going in, the remainder is going to be 1, and that means that we're going to go back, and it's going to pull the temperature from January. So 13 means January, 14 means February, 15, and then likewise, 24, the remainder is 0, right? And so if the remainder is 0, 24 would be December of 2 years from now. See what I'm saying? So 12 would be December, 24 would be 2 Decembers away, and so on. See what I'm saying? So it's always going to be, this function is always going to return a number between 1 and 12, because it's always going to be the remainder after that occurs. Okay? So that's all this function does. So take this function, and you've got to do that. You got to do that twice. So now I'm in temperature. I say OK, and I got to put it in here. Except for here, I've got to take this to say precip. Oh, and I got to change this up here. So this has to say make path parenthesis percent value percent parenthesis. Okay, so this, what is this? All this is doing is saying run this little Python function and return the result. So you don't really need to know a whole lot of Python to do something, to use Model Builder effectively, but it would be very effective to learn to learn what you can do, and then you'd explore how to do that. So this is only, really 4 lines of code. So all you'd have to know is how to write a function, and then operationally how to get the number that you wanted, which is use the modulus operator. So it's called. So, all right. So you say OK. Now our function will work for additional values. The last thing that I'm going to do to modify this is to right-click and say make variable from parameter. I'm going to say from value, and make variable from parameter to value. Okay. And then I can say the from value is going to be start month. I'm not going to call it end month because it's not really the end month. Okay, it's just the end value. And I'm going to make both of these model parameters. If I right click and say that they're model parameters. So now the start month and the end are going to be model parameters that you can input. You can put those dates, those things in. Okay. So if I go ahead and save this, and in order for this to work, I have to delete my outputs in the folder. So I go back to outputs and I delete these data sets. I'm going to delete them. Okay, now I go back to the model, double click on it, and you notice the start month and the end appear right here. And the default is 6 and 9. I'm going to change it so that it goes 6 to I need to go all the way to May the next year. So it'll be 6 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Or, yeah, 18. That makes sense because that's 6 plus 12. If I wanted to go a whole year, 6 plus 12 is 18, right? It is.
In your model?
Yes. In my model?
Main parameters for, as far as input were 4, you went from value and to value.
Oh yeah, so here I went make variable from parameter, and then I chose the from value and the to value, exactly, right? And then I just renamed those start month. I renamed the from value start month, and I renamed the to value end. I can do that again real quick. You want me to do it again?
No, so we got it, but,
Okay, so save that, close it. I guess I didn't need to save it. Okay, so now we're going to go 6 to 18. And if yours failed before, it's probably going to fail again. But I'm going to hit OK, and it's going to process through. And then we can talk about solving additional problems. So I'll say OK. Actually, everybody can hit OK, and that way, when you get an error, you can tell me what your error says, and I'll try to think of what the error might be. So I'm going to hit OK. It's going to process through. It's going to take a little while because now it's going to run it a full 12 times. You could run this for, okay, I know if yours says cell size is not set, that's because under environments, you need to set the cell size. So set all that stuff up that we've been talking about, the snap raster, the extent, and the cell size. So that's one thing to remember. Mine just did that, okay? Set your cell size. Now hit OK. I got an error because I forgot to do it. Okay, so let's see if I get an error. If I don't get an error after one time through the model, that'll be good. That probably means you're safe. If it executes one time through. It's doing the cost distance mapping. Okay, it's calculating the values again for the second time. So we're getting precip 7 now. So we're one time through. Okay. All right. So on the coast, did yours execute or not? Second time through. Got an error?
I'm having problems with the, inside the model builder where
I'm gonna open up another arc map. Inside the model builder, I can show you the model.
it's not running temperature and precipitation into the growth cycle. So I don't know why.
Okay. So what you're saying is add toolbox. Bam. So if I edit this again, what you're saying is it isn't running this calculate value right?
I think it's running that right. It's not taking the temperature and precipitation into the growth cycle. I'm not sure why.
Are those connected? Are they connected like this?
Yeah.
What's the error say?
You want the code?
No, when you try to run it, you say you're getting an error, right? Or is it not even running?
It says temperature data set and file name does not exist or is not supported.
Okay.
Unless for both temperature and
Right. Okay. So the things that I would check for that are, it sounds like it is creating an output. It is creating an output here, and it's passing that output from the calculate value into this circle, and that is being passed into the growth cycle. But the thing is, the value that it's creating, the path that it's creating, isn't actually where your data is. That's usually what that means. And so, did you? So the error that you got said something like that. That's when you actually ran it, right?
can you open up where it says calculate value? I didn't have where the code was. I had, for some reason, an extra for the code. Can you open up calculate value too?
Okay. Looks. These both look exactly the same, except, whoops, except for the word right here that says precip. Other than that, the two should be exactly identical.
Yeah, I didn't, or I don't have that one. I didn't see where you did that calculate to.
So yeah, your path will be different. How about you? What does your error say? So here, let's see if this is still running, but oh, there we go. Let's see how far along we are here. We're back at precip 6. We're almost done actually, because we're getting back to the beginning. Precip 6 should be the last one. Let me show you how I might be able to, or I might go about replicating the error that you're getting here. All right, it completed. Just to show you how exciting it is, we'll look at the output. The output, the final output was 12 because it went through and did it 12 times. So there's the full extent of where it got after the 12 months. Okay. All right. So let's try to run this again. I'm going to run this model. Actually, I'm going to edit it first. See, my theory is that there's something wrong with this path. For example, like if I misspelled climate, I didn't put an E there, and I said okay, and I saved this, and I close it, and now I try running it again. I hit OK. I'm going to get an error that says pretty much what your error said. It says data set C whatever does not exist or is not supported. I got that error because if I look at this path, see the path there? See the path that's listed there? Before that that message, it says does not exist. This path right here, I have to make sure that path really does exist. C:/lab data/ I misspelled climate data. I spelled it without an E. So when it tries to find it, it says, I can't find it. It either doesn't exist or it isn't supported. And so I'll go back here, edit it, and make sure that I didn't misspell anything and my path is correct, because your path is going to be different. You're not going to type C:/lab8/climate data. Well, it'll be /climate data, but yours might be some other location on your disk. Okay, so now I'll save that, and it should work. I'll leave that open for a second. So that's the first thing to try. Let's see here. Did you ever get it working?
It's working right well. We'll see.
Well, if it's run through one step successfully, it's probably. Did you guys get it to work? So you're doing some effective day off work. Was that a segue that guy was right in front? All right, you're still building it. Yeah, if you want to, on the coast, if you want to take your toolbox and save it and email it to me, I could look at what's wrong. Now, of course, if the path is what's wrong, then up here it's going to be wrong. I mean, every computer you go on, if you put the data in at a different place, it'll always be wrong. And so, you know, if you were to do this, if you wanted to be really fancy, if you were to do this, you might create a variable and say that you wanted to create a variable that was, let's say, a folder, because you can do that. You can create a variable that's a folder, or what's sometimes more often used is a workspace. A workspace can be a folder or a geodatabase. That's what workspace means in the ArcGIS world. So if I had a workspace here and I allowed the user to choose that workspace, I could make that a model parameter. See, I made it a model parameter. And then inside here, I could choose the default workspace, which for me would be this outputs.gdb. That would, or sorry, the climate data. That would be my default workspace where I wanted to save it. And then I could do something like rename this one, you know, workspace, WS. Okay. Then enter my calculate values. I could do something like, say, comma, percent, WS percent, and do something like this. Again, you don't have to do this. It's just showing you that you could. This is how you would allow the user to select the workspace. So if I hit OK now, and I hit save, and I close this. Now I'm only letting the user choose the workspace for one of the two data sets. I'd have to change both to get it to work for both. But now when I run my model, I can choose where the data is going to be, so that the user is allowed to choose that, and wherever they put the data, it works for them. I won't run this again because it'll run a lot.
So
Let me look here.
for the file under calculate value, you have 5A climate data into your database temperature.
Yes.
I have to find my file, which will be under my drive that I copied.
That's right. You copied from the U drive, right? I'm just going to put mine back so that I can help more effectively. The best place to find it is actually in our catalog. Although you can find it in Windows. So if you go to Windows Explorer, you could find climatedata.gdb, and you could copy that path. So copy that path. That's the path that you need. But to verify that those data sets are actually there and they got copied over right, you should look in our catalog, which our catalog is kind of like Windows Explorer, but for looking at GIS data. So if you go down to climate data, and you have to make sure that all of your little data sets are there. Okay, all your data sets are there. You can look at them. It's kind of interesting to. Here's February, March, April, May, temperature change or precipitation changing throughout the year. All right, and then getting to the last question, what if we want to, the last question in the lab, modify the model so that during each loop, a table is created that displays the total affected area for each state. How do we do that? Let's go back to our model for a second. Again, this would be something, this is this output is the total affected area total. So what if we want to find out the total affected area in every state? By state. What's another way to say that? Why I put it in the lab. A state is just a zone. So you could put a zonal statistics as table right here. Okay, zonal statistics as table, you just put it right there. Make the inputs the appropriate inputs. What are the zones going to be? Zones are going to be the states, exactly. What are the what's the zone data set to summarize going to be? The the output. Okay. Now if we do the zonal sum, what's it going to tell us? The number of, because it's all ones, right? So what's the zonal sum going to tell us? Right. So if I get a value of 1,000 for South Carolina, what does that number mean? It's the sum of all those one values. Every cell had a value of 1. So what does that value of 1,000 mean? What if all the values in every cell were 10? What if they were 5? I mean, but they happen to be 1. So every cell has a value of 1, and I'm asking for the total of all the cells. So cells, yeah, I mean, you can be used to get the area of the cell, but if I'm just getting the count, right? Every cell has a value of 1. And so if I say the zonal sum of South Carolina and I get a value of 1,000, the 1,000 cells are inside of South Carolina that have a value of 1 because the no data cells aren't added up, so they're not included. So if you have your zonal statistics as table, every state is going to be a zone. Not every state's most states are going to have no data. Okay, only a few states are going to even have data in them. And those that do, the zonal sum will be the number of cells in that state that are affected. And so you could convert that to area by just multiplying all those values by the cell size times the cell size. Cell size is a linear unit, like one side of the cell. So let's say the cell size, well, let's find out what the cell size is, because we might as well. Did I lose? So the cell size is 5,000 by 5,000. I don't know why. I thought I made it 5,000 by 5,000, but evidently I didn't make it quite that. So 5,000 times 5,000 times the number of cells is the affected area in that state. Okay. And the reason why it's 5,000 by times 5,000 is because I want to talk about an areal unit. So if it was, if it's 10 by 10 square, I'd say 10 by 10 times the number of cells, and let's say there were 50 cells. So 10 times 10 would be 100, times 50 would be 5,000. So 5,000 square units, whatever those units were.
Is that meters?
That is meters, sorry, yes. Meters is accurate right down here. So if you look at the projection, I think it does say in here, yeah, linear unit meters. All right. So did it ever work yet? Okay, we can take a look at it. How about on the coast? Did it ever start working? What's the error now? Say the same thing?
Mine ran through. I changed back across. Didn't have a error code. The green bar, you running it, and what I look through.
It never what?
The green bar, you go, it's right in the bottom.
Yes.
It never never filled all the way. It was like almost halfway.
Almost halfway.
I said flow cycle. My model, it stops right after calculated value, the temperature and the condition. It shows that they ran, it's got the shadow behind it. But then growth cycle, source, and output are, they don't have any color. They're just white boxes.
Okay. Now, are your do you have lines here? These preconditioned lines? Do you have those? And do you have these lines that connect into the growth cycle?
Yes.
Okay. And
It's like it ran all the way to growth cycle and stuff.
right,
There's no error there.
there's no errors, but it ran there. It ran to there. Okay. Well, is growth cycle still white?
Yes.
Was it white before you ran it, or had it changed colors?
I think it was white before I ran.
Okay. Yes.
Changed the calculated value.
So double click on growth cycle for me on your screen, and read me the values that it says in temperature, precip, and source.
It says temp, precip, and source.
It says that right there, like mine does. What does it say for output?
I
Say,
have an X, like an error warning.
What
on
it-
source.
what does it say when you hover over the X?
This output 4 does not exist. Or not stored.
Output what?
4.
I'm sorry, I still didn't understand that word. So, the air conditioner's on up here.
Output 4.
Output 4 does not exist.
4.
Does this say output 4, or does it say output percent in percent?
Percent and percent.
Okay. Now, so it ran. Does this path exist? This path has to exist too. So in other words, you have to have an outputs.gdb.
It's got a warning. Little yellow sign about that one. And it says it already exists.
Oh, okay. Well, if it's not an X, that's not a problem. So if it's a red X, it's a problem. If it's a warning, it's just telling you that that it already exists. It's already there.
Yeah, but I still have the red X across the source.
Oh, by source. Okay, sorry. So yeah, the red X by source, that's the problem. So it's saying that it can't find that that value. So if you click that and go back to source, okay, open up source for me. And do you have a red X there as well?
Yeah.
No red X there. Okay, go like this. Go.
I think it's that source bubble has the output for it from the first time we were running through our growth cycle model.
Yeah.
So I'm going to change it to source from climate data.
Yeah. Yes, you want it to be the source from the climate data. That's what you want it to be, because that's the initial condition the first time through the loop.
Okay, that's color now.
That's color now. Now, hey, if you take the source bubble and you move it, is there another source bubble behind it at all? Sometimes that happens.
Just that one.
Okay, good. All right, well, if it's green, then try running it again. I'm not going to say it's going to work, but it's you've conquered one problem. All right. Let me know what it says. I'm going to see here if I can help somebody. So your alpha just didn't look right? For the rain?
It just kept running and running and running. I mean, it was like, this is for this.
Oh, okay.
Alright, so didn't get an error that said it's not there, right? You just want did, yeah, now if you run it from here, you're gonna get it. You have to run it from there because you have to be able to set the environment. Well, you said it just runs and runs and runs forever. Right? Okay, well, yeah, go back to that for a second. Like on it, edit it. So that should change each time, right? Oh, that's right. Yeah, this one, start from. And this is putting your output into your climate, into your climate data, which is fine. I just organized it. Let's just go 6, 7, 1 time through. It took, I mean, this, like, I don't know. Doing the cost is long. Yeah. I think that's what I was kind of paranoid, like, with the output, like, 6,000. Right. And as soon as, so I guess me going back into my. And that succeeded. Let's look and see what looks like. Output. I mean, it is doing a lot of operations. Mine took a few seconds. So we just did like 2, 3. Looks like it ran a bunch of times before. Okay. Let's see what this looks like. I mean, mine just like letting it stay for a little while. Yeah, that's fine. So and if you're waiting for it, I don't know. Now I'm starting to like output. Yeah, well, it's not gonna actually show up. Okay. I mean, at least when you mine. I added that too. So now we'll do up to hurry. What's and it does take a little while. You want about 18 years. Yeah, this is 3 sub 6 started, and then probably was like a second. Yeah, it took mine. Remember what I did was I opened up another arc map and I kept talking. So maybe that's why you can see. Oh, okay. Yeah, it just didn't. Yeah, I kept talking and then I went back to it and said, hey, it's done. So it does lock the current arc map down. So. All right. So yours was working, and I'm pretty sure yours was working. You just hit cancel early. All right. What type of error are you getting now down there?
I'm still running.
You're still running. That's good. If it's gone through one cycle, it's a good indication that it's probably working. Okay, okay, great. It did take me about 10 minutes. What I was just saying here was he thought his was on an infinite loop, but remember when I did it, I opened up another arc map and I kept talking. So it's probably working just fine.
Whenever you double click on your model, your box.
Yeah.
It has start and end. We're gonna put the numbers,
Right,
if you put 6 and 18.
right.
It's the same thing if you put it in the model. If I look it up, start model.
Yes. Yep. So anything where you right click and you make it a model parameter, it just allows you to change that value right when it runs, and it's the same as it being put into the model there. Good question. All right. I'm gonna go get a drink of water. I'll be right back. If anybody has trouble, still has an error, let me know. And if you just give it a few minutes, and we'll see if they finished right. So I think that is a segue, right? Did you all learn anything? Right back. Okay. You guys work.
Yeah.
Whatever you said. So
Here's your Python stuff. I finished 5.8, and I'm gonna get it, and I was trying to do like 9, and I thought I had it done working perfectly, but I ran it again, and this crashed. And then I ran it again, and it crashed. And then I ran it 4 times, and it worked again. And then I ran it again, and it crashed. I didn't know. Like, I don't know what's going on. The error is different every time, like. Yeah. But I think I'm gonna do. I haven't started on it, but I know what I'm doing at least. I'm gonna take my data points from all my fire stores, and I'm gonna make a polygon around each of the I guess representing each fire that happens. It's not how great it really is. I don't know, but it's a shot. I can throw that. I want to throw that in my thesis too. Like, I gotta do that for weeks. But something. Yeah, I'm done. I'm right now trying to run my time analysis. It didn't come out very well, so that's one of the things to try to. I guess we'll see if that works. But other than that, what I basically found out is that climbing has nothing to do with fire and this is so that's the story. you got this thing where people can run. Pretty close. So,
Yeah. Well, okay, so when we first started the lab, this is from what we started, like this, we were just, the first step in terms of lab thing, building like this spread. So that's the museum, that. So, running to
Did it run or no?
yeah, grams right there. Okay.
Did it run down on the coast or no?
So,
Still running. Wow.
I give up.
You gave up. Was it running and you stopped, or was it? Did it have an error that
There.
you can't get past? Why don't you send your toolbox to me and I'll look at it. Send it to me by email.
Which one?
Just the toolbox, the TBX file. So go save it, close down ArcMap, and then navigate to the toolbox file, the .tbx file.
Which email?
Oh, yeah, send it to my regular my george.raber@usm.edu because the other one I don't check as often. Thanks. All right. Thanks.
I've learned, like I've said here with Sean, I'm learning about this I didn't learn with Dr. Carr. That how many
Questions about, okay.
Did you send that toolbox yet, or I don't see it on my side?
Not yet.
Okay.
That's why I'm sending the house. Right?
Hey Bryce, check it out. You know what this is right here? There you go. That's his older brother, my 15-year-old. I got to figure out how much that's going to affect my car insurance. What's that? Did Joe get his?
It's just interpretation of okay, so I did lead, and that's for most of this. Okay, so what, so form or sort of interpreting what I'm seeing, and then also math. Oh yeah, good. So basically, what I mean, most of the variation I'm seeing is right, and toward the edges, because those are the areas with less, less interpolation possible. No points over here. Okay. And then as for math, basically these, all the ones we can. Right. Yeah, it's like 5 maps. Yeah. The one eyeball and that one I did line because I get like really off. Yeah. It usually is. Okay. Now, the colors don't really mean as much as but that's sometimes why I ask you to do the difference now. Yeah, it's fitting a rigid sheet through all the data points. Sometimes you have 2 points that are really different right next to each other. To fit a rigid sheet through are steps are like really different. Sometimes to put a rigid sheet through, it's got to bend up something crazy to do it. So it gets some pretty crazy.
And also, you talked about the screen capture.
Yeah, that's an option.
For some reason, like with this, I've got functions that go screen. I guess it doesn't.
You, what is this? Windows? I know, I have one here. So this tool right here, called the snipping tool, comes with Windows. Hit new, and you can draw a line. And that puts that on your clipboard. I know it's on there, and even if you didn't do anything before, you know it's just a copy. You can change it or super snipping tool. All right. But that's easy. You can also just go file export an app and go export it.
Okay. So in my description, my paragraph, basically just mentioned that, okay, most irrigation occurs have but also points are
Yeah. Further away from the other edges.
Whoops. All right, let's look at your toolbox and see if we can work through this. Copy.
I just put the file names. Now it just needs to set where the cell size and all that stuff is. I think that might be the problem.
Yes, you do need to set the cell size. That is true. Oops.
I think I might have got it back to where you were. Just give me a second.
Well, that's great. Your model does look pretty good. Is your yeah, I'm just fixing.
That's what the problem is. The
Okay.
problem I had to put in lab 8/data/that. For some reason, whenever I copied it out of the file properties, it didn't have that, and I don't know why.
So it is working now.
So Kathleen, it is working now? Can you guys hear me?
Yeah.
It is working now, or?
It's running and it's not showing any errors yet.
Okay.
So I'm thinking that it's going to run through.
Yeah, it used to be 2 years ago, you all had newer computers than we did. And I think that you're on a cycle now where you have slightly older computers. So it
might take a little bit longer than it did to run up here. But if it's running and it's kind of hard to see, but as it's passing up, if that number, if you ever see a thing that says precipitation underscore and then a number, if that number is increasing, it's probably working. What's that? Yours ran all the way through. Did it work?
Yeah.
All right, great. Well, good. All right, well, let me know how it works for you too, Kathleen, and then we'll be all set. I've got a couple of students here that want to talk to me, but I'll be back and forth. Pop in here in a second. Taking pictures?
Small. It's not damp, it's wet. It's not too rough. That's why you say all the time. Oh yeah, our time crashes. Yep, yep. Whenever you finish something, you say it. Toyota. Toyota. She been here? Yeah. Yeah.
This is it. There's an online. For a year, or for a month, I just. Overall. Is Dr. Brazil there?
Dr. Raver. You need Dr. Raver?
you get, what this is, ESK one?
No idea.
Whew. Nice and cool in here. Did it ever run for you?
Yeah, I ran, but it only came up as like one layer. Was this supposed to do more?
The final layer is all that matters. So if the one layer was a blob that looks like this, something similar to this one, but just a second. I'll put 12. If it looks similar to that, then it's probably right. But what probably happened if you only got one output is that this, sorry, yeah. So this is actually your copy, and unless you changed this, because you did say you changed a few things, this needs to be changed so that it specifies a path, but at the end you say % and %, and then each time through it will change its path. Does that make sense?
Yeah. I had did that, but for some reason it changed back to what it was prior. I'll do it again, I'll run it. And I also have another question for
Sure.
you. Whenever we are, do you want us to make a line graph? And is that supposed to display every single one?
Yeah, I guess you're right that you do need to get the individual months. So where's this line?
It's at the very end in bold.
Yeah, turn in the toolbox on a line chart showing the area affected over a 1-year period for North Carolina, South Carolina, Tennessee, and Virginia. Yeah, so you do. I guess I said that it was important that the final output was there, and it is. But you're right. You will need to fix it so that each time through the model, your outputs are there, so that you can calculate this: North Carolina, South Carolina, Tennessee, and Virginia.
So you want us to fix this model to do it, or do you want us to just do it manually like we were doing it before?
Actually creating the model, creating the line chart, you might have to do that manually. You probably could, if you spend enough time and massage the data to make it output. But what I would do is, so here's the model that I created. Right here. And this looks similar to the model you created, but the difference here is that here at the end, I have this output n%n. And what you need to do is to do that zonal statistics. And the output of the zonal statistics data set will tell you what the area is in North Carolina, South Carolina, Tennessee, and Virginia. I think, were those the 4 states?
Yeah, you want us to note them individually?
But here, I'll show you what I mean. So if I to put them in the chart individually?
Yeah, like to say what the area is per month of each state?
That's right. Now you don't have to, you can put them all on the same chart, like you can make 3 different or 4 different colored lines on the same chart, or you could do 4 charts, either way. So here's the zonal statistics as table. If I drag this in to the model, and at the end, I could say, hey, I want the output to be the, oops, it's the wrong one. Feature zone data is always going to be the zones, the states. Oh, U.S. states. The state name can be the zone field, so that you'll see in the table for every state, it'll tell you what the value was in the output. Output table. And then I can call this output table. I can also store that in the same directory, the outputs directory, and call that something like table underscore percent n%.
But the %n% is necessary for it to distinguish the different,
Months.
yeah.
Yeah, the different times through. So n is the first time through ends 0, second time through ends 1, and so on. Yeah, exactly right.
Okay.
Okay, you want to make sure that this stays checked. So ignore no data values in calculations and say okay. So now once I have that, I should be able to run this. So I'm going to save it and close it and run it. I'm just going to run it through once and see if it worked. So I'll go to the temporal modeling lab, look at my model, go 6 to 7, make sure my environments are set. Cell size. Whoops, not as specified below. Needs to be same as one of these temperature grids. Okay, so let's see if this works going through once, and then I'll show you in the result where you can get this area value. So it's running, and the new thing that it's doing, coming up here in a second. Cost distance mapping is the thing that takes the longest. That just finished. So did that zonal statistics right here. And so now we could probably see, if we go to the outputs, there's my table. So here, my output table, I only have, I told it to use state, and it looks like that's a code. This is North Carolina. So in North Carolina, I only have one. Sorry, North Carolina is the only state that's got any so far. And so that's why I only see that that one data set in that. So now it ran again, and now I've got two states, state 37 and state 54. I should have paid better attention. U.S. states. So 37 and 54 are, 37 is North Carolina, 54, or is that, you said 40, you said 45, not 54, sorry.
Maybe I was wrong.
Oh, look. 45, you were right. Oh, but it's not this object ID column, it's the state column. So if you go to state, right here, sort this. I should have done it by name, not by state. That way it'd be easier to interpret. But 54, or 45, you're right, is South Carolina. So after 2 months of running, it's only in North Carolina and South Carolina. So if I ran this model a bunch of times, it's eventually going to get into some other states. But what you could do is after each after this runs 12 times, you'll have 12 of these. You have 12 of these tables, and you could copy those values into Excel. Okay. Here's the area values. If you want to just copy the area value right into Excel for each of these states. So what you'll have is you'll have all 4 of those states. So you have 4 rows, and then you'll have columns for the area after 1 month, 2 months, 3 months, 4 months, 5 months, 6 months, 7 months, 8 months, 9 months, 10, 11, 12 months. And then you can graph those. That make sense? Or
yeah, for the area, is that a raw number, or do you have to change?
the area number, because the areas are no data, this area number is actually correct. So you can use that area. Older versions of ArcGIS didn't calculate the area automatically. And so that's why I was saying that if you take this value here, 355, and multiply it by 5,000 by 5,000, then you'll get this number. Well, it won't be that exact number because if you remember, the cell size isn't exactly 5,000. It's like 4,999 and some change. But it would be really close to that number. But I don't care if you use 5,000, if you round off, but you might as well just take this number. But that's a good question because it's there for you. When I was talking, I said you have to multiply that sum number out, but I guess you don't technically have to do that. Okay.
Can you look at the calculate value inside the model? If you open that up.
Yeah, that's okay. So this guy. All right, and then this is the zonal statistics. I know I realized I went through that probably pretty quick, but that's all that's doing. And then I might actually change this to name if I was going to do this again. So I hit name. I'm not going to run it again, but if I change that to name, it'll be nice and say South Carolina, so that it's easier to copy those numbers in.
Okay, I don't know why this isn't working for me.
The zonal statistics part or the whole thing? It just runs, but it only provides one output. It's not output whatever, output whatever.
I think I might have. Let's see if I can. Okay, yeah, so I did get 2 tables. Yeah, I still have to keep on doing this until you said I get 12 tables so that I can show the difference in numbers.
Yeah, so if you got 2 tables, that's good. What you want to do is just run this again, but instead of, so if I go to geoprocessing results, I just made it so that it ran 2 tables so that it didn't run a ton of tables while I was demonstrating and I could look at the results. But yeah, if you go back and run this again, but now you go from 6 to 18, it'll produce all the tables that you want. It'll produce 12 tables and you'll be set.
Okay.
So now if I hit OK, I'm not going to do it. If I hit OK and just waited for 20 minutes or so, all the tables will be generated that you need.
Okay.
All right. All right. I've got to head off, but if you need anything else, let me know, and we'll be back in class Tuesday. You can always ask questions then. Finish the Hangout. which I should have done a long time ago. Don't know why this